Thank you for having me here in the Lunch and Learn. Well, my name is Diana Gaméz, as Tom was saying. I work here in Code. I'm a backender developer in Recall and also a team lead. So what I'm going to show you is the facial expression recognition using deep learning neural networks. So let me share my screen so you can see one small slide that I created. Can you see my screen?
Yeah.
Okay. So first of all, what is facial emotion recognition? That I think is the most important thing, because we are going to start talking about this and we need to identify first what is facial emotion recognition. So this is the task of classifying different emotions, different expressions, depending on categories. Darwin identified 7 different basic emotions that are fear, anger, disgust, contempt, happiness, surprise, and sadness. There are some specific special description for each emotion. So that's how Darwin described it. And that's how we use it for this example to identify these 7 basic emotions from people's faces. But we have to go back a little bit also to define what is deep learning. Many people, I guess, you have heard about artificial intelligence, machine learning, and deep learning, but what is everything about? So artificial intelligence is anything that enables the computer to act like human people will act. And this is also including machine learning. So machine learning then is a subset of AI that includes techniques that enable machines to improve tasks with experience, like after learning. And then later so deep learning is a subset also of machine learning that at the same time is a subset of artificial intelligence, that specifically deep learning is based on neural networks that can train itself to perform any task. And in this case is facial expression recognition. So at the end is classification everywhere. How can we identify these emotions? With classification. So I'm going to show you a practical example that I created in the past. I'm going to first explain you how it was built, some concepts for you to understand what is the magic behind of all this facial expression recognition, how it was built, and then at the end I'm going to show you what was the result. So first of all, we start with the tech stack. We had TensorFlow because we wanted to build it faster, and also to create a model that we can later use with OpenCV. So we mix TensorFlow with Keras. That Keras it can run on top of TensorFlow, and it can help just to create this artificial neural network. Then we use OpenCV because this software is identifying the facial expression in real time. So that's why we need OpenCV. And then we need Jupyter notebooks. And we use Collaborative. That is a free Jupyter notebook that is provided by Google. And this is really powerful because it has a free GPU. And in this case that we are using a lot of images and we are training a model, GPU is always really good. So because we were building an open source library, we wanted everything to be open source and open to the public. So that's why we're saying that let's use Jupyter notebooks in collaboration with Collaborate, so we can have a free GPU to train our data model. So how did everything started? There is a data set that is called the FAIR 2013 data set that it came out of a competition from Kaggle. Probably many of you have heard about this page, that they create many competitions related to data, artificial intelligence, and so on. So they opened this data set to the public so everyone can use it. It contains this amount of images, that are 30K images with different emotions, that the 7 emotions that we saw before. So the thing is that it's grayscale images that they provide different people doing these kind of faces to identify the expressions according to everything is labeled already. So you know that building a data set is really difficult because, for example, in this case, you have to go there, ask too many people to perform many different expressions and then label everything. So having this open data set is really good because at the end you can use it as a baseline and then train your own model. So after this, so once we had all the data sets, the data set and also tech stack, then we can move to what is a convolutional neural network. Because we were talking before about deep learning, but the most famous process or to identify the images nowadays is the convolutional neural networks. What is this? It's part of the learning. Again, it's an algorithm that it uses an input image and it assigns importance to various aspects of the images. It's just like the brain, because actually this was inspired on the visual cortex of the human brain. So for example, when you identify something, if you remember the face of one of your siblings, probably you will remember that he or she has black hair. And there are some specific aspects of the face of your sibling that you remember that makes you remember this person. You don't remember everything specifically. So this is what it does. It's trying to identify the important aspects of the image. Then later it can be used for image recognition. So the role of this is to identify, to reduce the images in a form that is easy to process without losing the features, because features are really important in this, but not all the features are important. So, okay, we have an image and we have our convolutional neural network that we are gonna see later how is it built and all the steps that you have to follow and the actions in the process. But of course we have the data set, but we need to prepare this data set in a way the computer or the algorithm can understand. So this is an important step at the beginning of all this process that is called data preparation. What is data preparation about? We resize the images, because probably imagine that you are taking a lot of images or pictures with different cameras and you don't have the same size. So it's gonna be difficult later to process all the images or to analyze all the images inside of this convolutional neural network. So it's important to resize the image so you make sure that for the algorithm it's easier to identify all the important features. Then you can normalize the pixels. Also, you can crop the images, because probably you have like a landscape behind the person, but you don't really want the landscape. You only want the face of the person. So you have to crop, flip the image. There is, because we were saying before that we use Keras, there is an image data generator that can do it for you, and it has a lot of tools and interesting parameters that you can tune, so you can create this. So it can pre-process these images and create tensors. So remember, we were using TensorFlow because TensorFlow is based on tensors. Then the input of the image, the image will be converted in tensors, so it can be read by the convolutional network, by the network. So this phase is important because later we will see about the overfitting. But we will define the overfitting, and you will see why the data preparation is important also in the process. So once we have the data and everything, we have to start building the model. So there is all these layers, and all this model is called the sequential model, that at the end is a stack of layers that we have. Each of them receive the input shape, and then it converts these specific or more important features. So later you can classify them. So the input shape, it depends on the width and the height of the image. That's why I was saying that it's important to crop everything at the same size. And also the channel. By channel, I mean the colors. For example, in this case, we have a grayscale images, so we only have one channel, but imagine that we have color images, so we will have 3 channels, red, green, and blue. So the second step will be compile the model. So once you extract all these important features, then you have to train one model, so later to classify the emotions. And then after that, you fit the model. By using the data, you train the model many times to learn. It's like you show a picture of a cat to a person, and then another picture of a cat and a cat and a cat. And later this person will know that that's a cat. If later this person sees a cat on the street, then it will identify that it's a cat, because this person has seen many different pictures of a cat before. So in this step that we were saying, if we recall, we were saying that first we need to configure the sequential model. That is a stack of layers. So we have two different layers. One is the convolutional layer. It's just a fancy name because it's not that difficult. But what it does is it extracts the high-level features from the input, and you go from one layer to another one, and you are extracting the more detailed features. So how do you do that? By using a kernel that is a small matrix of numbers that is creating an image convolutions. Image convolutions is like transforming this, so in a way you identify the main features and you can transfer to the next one and to the next one. So of course, because we have color images or grayscale images, it has to have the same depth of the input image. So from this operation, we have two different results. It can be depending on the padding. I mean, I think many developers know what a padding is, but we can have two different paddings in this case. We can have valid or same padding. So this is an important tip. So if you have to select the padding. So the valid padding is gonna reduce the dimension of the images. So it can create loss of information. But for example, if you have some specific thing that you want to identify in the image, probably the valid padding is gonna work for you. And then the second one, we have the same padding, that basically the image remains the same dimension. And it applies normally to all the elements. And normally in this, image recognition is the one that is used. Actually, in this project, we use this one. So the second part of the layer is called pooling layer. Because we are working with a lot of data, we need to decrease the computational power to process the data. So this is the responsibility of the pooling layer. It is in charge of extracting the dominant features, not only the most important ones, the dominant ones. And in this case, we have the max pooling layer and the average pooling layer. But for this project, we use the max pooling layer because it removes the noise of the images and it also performs better. So my suggestion is to use max pooling layer, but it also depends on the case. So why am I explaining convolutional layers and pooling layer? Because the sum of the pooling layer plus the convolutional layer, it will give you the layer itself. And there is a lot of questions around this. Like, if I'm building a model, how many layers, or how do I define the number of layers? There is actually not like, I can tell you 3 layers and your model will be fine. It's not like that. It depends on the complexity of the images. So of course, the more layers you have, the better, or the more detailed features you will have, because you go through different layers and you extract different features. But also at the same time, it becomes a little bit heavy to process. So it's just a matter of being like, start creating just like a test or something. Like, you see your images, you see, like, by adding 1 layer more, the game becomes rather small. Then you will need to decide if generalization accuracy is what you want, or training time. Because if you have more layers, then training time is gonna go higher. So there is not a specific like 3 layers and that's it. So it depends on your problem. So after we extracted all the detailed features, we have this flatten. This flatten, what it does is the features are contained in a matrix. All the features are there, but in order to be like to pass to the next step, that is gonna be the fully connected layer or dense layer, that is later gonna classify all of these images. So you have to flat this matrix into a vector. So it can later be the input of the layer of an artificial neural network. So basically is what it doing is in the middle of your convolutional layer, you will need a flattened layer. So later you can go to a fully connected layer. You can stop me at any time if you have any questions, because probably sometimes it's a little bit too technical, but I'm trying to do.
I got one question, Diana, with the pooling layers. I didn't understand exactly what it does. So it takes what is the left from when it's coming this? It's the pixel information or something like this?
The pixel information. Yeah.
Okay.
So the first one, it was getting the more detailed layers, and this is like the more dominant features.
Okay. 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 Thank you.
So after we already have a vector, we go to the dense layer. That again, it can be called fully connected layer also. And every input is connected to every output by a weight. This is important because later we will see why. And is generally followed by an activation function. An activation function is the one that decides which neuron is going to be activated. So the first parameter goes inside of the neuron, and then it produces an output that is going to be a weight. So the weight will say how relevant is this information or not to go to the next one. In this case, so the output layer of this fully connected layer, I mean, the output number of neurons will be 7 because we have 7 different features. So it will be a classifier between 7 different features. So we were saying before about the activation function. So this is the most important part of the neural network, not the convolutional one, because it decides if a neuron it gets activated or not. So it basically means that to check if the input is relevant for the neuron, so it gets fired, and then it goes to the next one. It's like you have a river, and then you cut this, and the water cannot continue anymore. So normally the one that is used is the ReLU function, because this basically has 0 or 1. All the negative values will be converted to 0, which means that it's not going to activate the neuron and it's not going to go to the next one. And if it's positive value, because it's really valuable the weight, then it's going to go to the next one. It's just activating one neuron on the other one. I don't know if you have seen like these images that has a lot of colors that is with neurons and activating one, and the other one is basically that. And it's doing that, like the meme says. So I want to go to the next layer, but really saying, no, you're not going there because you're a negative value. So after you have this of how to activate or not these neurons, there is also an optimizer. There are many different optimizers, probably, or maybe not. You have heard about gradient descent. So it's basically this, and you have seen this kind of graph. So what we are looking here is to get to the global minima. So we make this algorithm to learn faster. It's basically what we want. How can we make this algorithm to learn faster? Well, with an optimizer. So an optimizer can have many different things, including a learning rate. So having a high learning rate means that you learn faster, but that doesn't mean that you are going to get to the global minima. But having a lower learning rate, that doesn't mean that you are sure that you are going to get to the global minima, because it's going to take less time. So imagine that you have mountain that has water and is going down, but you want this water to get to the lake, for example. I don't know if a lake is next to the mountain, but in Mexico it is, so you have to believe me. So you want this one to go to the lake. This will be the slope. So the water will go down till the lake. But probably imagine that there is one small lake before. So if it goes that fast, then it will stay in that lake that is the small one, but it's not the one that you want. It's not your final destination. But that doesn't mean that if you go slower, then you will get to the final destination. So this is the learning rate, thinking how fast your water goes into the lake. So, and then going back to this, it reduces like the various good and bad aspects of, of how you can learn faster. So why am I saying about the add-on optimizer? Because there is like momentum optimization. There are many optimizers, but in this case, there is this add-on optimizer that was created in 2015. Actually, it's pretty like recent. And people have been using this for image recognition. So it takes like the best of both worlds, because you don't have a fixed learning rate. So you're adapting your learning rate according to what you move. So imagine that your water is going down, and then it's gonna go slower because it sees that the slope is very, I don't know, high or whatever. So you are adapting this learning rate according to the previous step and the next step. So that gives you a little bit of more certainty that you are gonna get to the global minima. But at the end, the goal is to get to the global minima. So also another advantage of this one is that it requires less tuning of the learning rate, because people say that the default value will be this 0.001, and you're going to start with that one and then you can increase it. But because it's adapting this learning rate, at the end should be enough. So we have another meme for you to remember. At some time you're training a convolutional neural network, and then you say, oh my God, probably I should have used another learning rate. And they're training and it's going to take a long time. Actually, this neural network for the face expression recognition, it took like 4 hours to train in a GPU, because it had many different layers and many different pictures. But yeah. So then we move to this one, that is the loss function. The loss function is to evaluate how good the solution is, basically. So what it does is like, what's the probability if I'm smiling? What's the probability that I'm happy? So it's gonna say like, yeah, your probability is really high. So it calculates the probability of each example belonging to each of the classes. In this case, we have a multi-class classification problem. So it normally you use this one cross entropy, and because we love to see maths, not because we understand that, that's why I put that one in there. So, but before the cross entropy loss, you normally have this activation function, as I was saying before, the sigmoid or the softmax or the ReLU. Remember, this activation function is we activate the neuron. When you activate the neuron, then you calculate the loss function. Then, okay, that's like one flow, but then it has to be repeated, because it's learning like the same way we learn. For example, how do you learn to read? You have to practice. How do you learn to run? You have to practice. How do you learn to do whatever thing, or a word or an image or whatever? You have to practice. So this practice, every time that you practice, is one epoch. So there is one time that probably you have seen a lot of times the same picture of a cat that you already know that is a cat, and you are not learning anymore. So that's why it doesn't mean that if you have high number of epochs, you are going to learn better, because probably there is nothing more to learn. And then the batch is how many images, for example, someone is going to show me about a cat in one epoch. And then you have everything, and everything is working correctly. You start training your model, and then you see this. This is an example of an overfitting. Remember that before I was telling you an overfitting, well, that we could avoid overfitting. So overfitting is this. You are performing a really good at training. So you are identifying everything. You are the pro one, because you know what a cat is, but you have seen only red cats. So what happens if I show you a white one? Then you don't know what it is, because you learned too well about a red cat that you didn't know about any other. So then you will see this kind of graph in the result of your model, that it will say, yeah, well, I was learning fine. No, you weren't. So
one question, Diana,
yeah.
you have to send pictures of not a cat as well, or it's not needed?
Yeah,
for
you
the
can.
model?
It depends on what you are doing. If you have a classification problem, well, you have to send. You can send only images of a cat, and whatever you see that is not a cat, then you won't identify it as a cat. You can also, it's like only one thing that you are gonna classify. If you want to classify and identify some object that is not a cat, some object that is a cat, then you will have to send 2 different images. Depends what's your output. So how this overfitting, then again, is like I learned too well to do something, but I only know how to do that. And I don't know anything else because I have never seen anything else. Probably I saw someone smiling all the time, that I'm not able to identify that someone is mad at me, because I have seen everyone that is happy with me. So I cannot identify anything else because I learned that. So how can we avoid this overfitting? We can either add more data, we can do some data augmentation techniques. Remember when I was telling you that the data preparation is really important. So these data augmentation techniques can fit in there. And you can also use an architecture that can generalize these like images too well. Like I don't only know that a cat has 4 legs. Imagine that I see a cat that has only 3. So I have to generalize that. So the first one is data augmentation techniques. It's basically applying different filters, rotations, translations, so on to the images. So imagine that we started with this picture of a dog, and then later applying data augmentation techniques, we have 12 pictures of a dog. So that means that you have more input. That means that not only this position of a dog will be a dog for you, also this one and this one and this one. And also if you don't whole face of the dog, is also going to be a dog for you, because you know half of the face of the dog. And this is a problem that we had, this overfitting, because this open data model, the first one that I was telling you before, it has few images, to be honest, to train a model. So it has few images in sadness, and we weren't able like to identify sadness properly. We were confusing sadness with happiness. And we had, initially we had 46% of accuracy with the overfitting. But then we started to implement this, and we got to 78% of accuracy, which is a lot. Then also the regularizer, what I was telling you, it also helps you to reduce the overfitting. It's telling you like, this is important, this is not important. That's it. And I mean, there are some mathematical things behind that. But basically, remember when I mentioned the weight is going to tell you this is relevant information or not. Then this is what it is doing. So we have the L1 and L2. That normally those are the ones that I have seen in image classification, but those are not the only ones that exist. So if you're trying to compress the model, so L1 can disappear the weights. But if you're not trying to do that because you have some specific features that are really like the difference between happy and neutral is really low. So probably you don't want to get rid of everything. So that's why we use in this one, the regularizer L2, because we didn't want to get rid of all the information. The next one, and the most famous one, technique to avoid overfitting, is dropout. So basically at every iteration, you are randomly selecting different nodes of your neural network. So it's removing and then put it again and all of that. So it prevents these units to co-adapt so much. So it's like, the way I see it is like, imagine if I go to the office and all the time I walk through Gran Via, and then I come back through Gran Via, and then at some point someone closes Gran Via. How can I go to the office if I don't know how to do it? So basically it's this, you don't get used to the input that came before and you don't produce the same output. So it's random. So it performs better. And then the next one will be batch normalization, which is reducing the number of training epochs, because it can standardize the input of the layer. So you normalize this to a range that is not like from 0 to 100, because from 0 to 100 is a lot of difference. So you normalize this, and it's better to identify how close they are. And the last one will be early stopping. Remember when I was telling you, you get a picture of a cat and you get the picture of the same cat, and then you don't have anything else to learn. So that means that you don't need to repeat again the same process. So you need to identify where to stop. So if you see here this graph, so you see that this line of the training and test is stabilizing and is going the same. That means that even if you go further, then you are not going to get another result. So probably it's better to stop in there. And that's how we improve this model and we avoid the overfitting. As I was saying, when I took over this project, it was 46% accuracy. And after applying all of this and a well-designed neural network, we got till 78. So the result of this at the end, it was a pre-trained model that later can be used in some other applications. So it's like taking your brain and creating someone else's brain. And what am I saying all of this? Because where is it used? You might say like, yeah, facial expression recognition, but where do you use it? Probably in a visual mirror, vehicles, and also military surveys and interactive videos. So there is a meme also. How are we going to make this facial expression recognition if we are wearing masks? This is the second. There are many challenges of this because probably the way I smile or the way for example, in Mexico, if you are neutral, that means that you are angry. So the emoji, the slightly smiley face is not actually that I'm neutral or I'm happy. That in Mexico, it means a different thing. So it depends, and that's it.
Super cool. Super cool. I'm wondering if people have questions for you, Diana, or everyone's like,
yeah. Like I fell asleep.
No, not asleep. I meant like blown away by the complexity.
No, super interesting. Really, really, Diana. That's amazing.
Thank you.
Yes, hi, Lucas here from Berlin. Thanks for the cool talk about how this machine learning stuff works. I only had a course in university ages ago and I have some idea, but definitely not so much deep knowledge. One thing that I would be interested is how you address biases in the data sets in your thing. You already mentioned that different cultures have different ways of expressing their feelings, and I guess the data set has a lot of more of these assumptions in there. So are you addressing this somehow, or how would you do this?
No, not yet. So what we are trying to do, well, when I used to work in that project, so what we are trying to do is also to implement other sensors, because with the face it's not like you can tell if someone is angry or not. So different sensors like the eye sensor, for example, because there is like the position of your eye can tell you how you feel, or also microphone to hear the voice of the person. So by implementing different sensors, you can give more accurate result. But for now, this by itself is not dealing with that.
Thank you.
Yeah.
I have one question.
Diana, I have one question. I'm sorry, Victor, go ahead.
All right. Regarding the model that you show right now, one way that I can think of to handle different culture data, it will be maybe having a classification for each culture, for example, like Mexican, Spaniard, whatever, and then some kind of multi-agent model, right? The thing is, how do you know the limit of the ethical predictions if you are?
Well, that's a little bit out of my range. And of course, there is like a different way you can prepare your data set. You can create different classifications according to the culture, race, or whatever. But as I was saying before, creating a data set is really difficult. So because you have to get a lot of people to take pictures from. So you're not going to travel to Mexico and then travel to Spain, to Germany to take pictures of everyone, all the world, and then classify that.
Yeah, I agree.
Sounds like quite a fun project. Count me in. But I mean, like what Lucas was raising, and Victor as well. I mean, that's one of the main challenges, I think, or the major challenges that's happening in this space now, in terms of like bias and this side of the kind of thing. I guess also just trying to get good training data sets that are really representative of the world population, right? That's the main challenge. I guess maybe we could start by trying to classify how good the existing ones are.
We can implement this for our employee satisfaction.
Nice. Yeah. Cool. Why not?
And yeah, it's really difficult because the most important thing can be the data set, but also you can have a really, really strong model, but if you don't have a good data set, then there's nothing you can do.
It does seem like these pre-trained models, once they're trained, like you were mentioning, right? You train it once, and if you have a good model, then that's it. You can reuse and reuse and reuse. I think it does seem like that's going to get pushed onto everything, you know, and you're going to end up with literally even dumb devices, knowing if you're happy or sad now.
I have one question. Once you have trained the model, what is the output that you have? I mean, you have a mathematical function that you can use in another place, or you have to still use like the same environment in order to determine if something is happy, someone is happy, someone is sad. I don't know if I'm explaining it.
Yeah, if you have like a small file, like your small brain, and of course, if you don't have the same environment, like black and white or a lot of light and a lot of things, it can also impact a lot on the prediction.
Okay, so it's not really exportable, no, to another environment.
Yes and no.
But the runtime I understood is, Albert and Diana, no, like the runtime, like if you create a runtime that's been trained, like you can port that, no? It's just
you can put it somewhere else in another application. So you can create your own OpenCV application with I don't know, improving the light or making everything black and white or playing with the video, and then you can insert this model and then you can start predicting. I think Jose had a question and we interrupt.
No, it was actually about the prediction, because when we were doing some researches, it was very interesting because there were some surveillance companies, you know, the security companies in especially public areas, they were recording the public, and they were trying to forecast the behavior. For example, if someone is behaving uncommonly, I don't know, faster or has a weird face impression, for example, angry, I don't know, the cameras were focusing on that person just to identify and avoid potential attacks or potential violence in the public. So I of course I don't know the technical details of this, but do you have any experience about this, or how does it work? Again, with images, it's a little bit easier to understand because there's a data set to analyze, etc. But the behavioral prediction, do you know how it works? Just because you understand from AI more than many of us, that's why I'm asking. Of course, if you haven't heard or know, it's fine, but
I have heard and I have read a little bit, but I don't have experience on that. I have never done anything related to that, to be honest. I know the theory, but I have never put it in practice.
So if anyone has, maybe next time you can give a lunch and learn if you know more, you know, prediction in terms of behavior analysis, etc. It's very interesting.
How much time takes to train an algorithm like that, and how many resources it takes? Because you have a big GPU to train those.
So we use Google Colab that has some free GPU, and we put our model in there, and it took like around 3 or 4 hours to train. Because we included a little bit more of layers that we should. So I guess that's it.
Seems like it, right? Diana, thanks so much. Super cool talk. It's always good to be reminded how stupid you are, and it reminded me how little I know in this space. So Yeah, congrats, but really, really nice, super interesting too. Thanks for taking the time.
Thank you. Well, I have a small data set. I only know about this and that's it. If you ask me about anything else, I won't know. So, but thank you. And it was really nice to be part of the Lunch and Learn, and I'm looking forward for the next one.
Super cool.
Thank you so much.
And hey everyone, anyways. Bye-bye.
Bye.
Thank you. Bye-bye.
Thank you.
Bye-bye.